Good evening, everybody. This is your video for your gas laws review for your test tomorrow. Okay, so let's get started. We're talking about states of matter with 1 through 3. This is very simple stuff. And when you're looking at this, we're looking at the words definite and indefinite. So let's start with solids. Solids have a definite volume and they have a definite shape. Any solid, definite volume, definite shape. Here we have a little cube. It's a definite volume, definite shape, doesn't change. Liquids, they have a definite volume. You can pour 10 milliliters of water into a graduated cylinder, which you did with your lab the other day. And it does not have a definite shape, it has an indefinite shape. It takes the shape of its container. Whatever container goes into, it takes the shape of the container. Gases have an indefinite volume. They can be compressed. They can be expanded. They also have an indefinite shape. They take the shape of their container also. Okay? So now we're talking about kinetic energy. And so number 4, KE stands for kinetic energy. Right? Kinetic energy. That's energy of motion. So with solids, they are, again, solid. So they will have a low kinetic energy. And if that's the case, that means their molecules don't vibrate very much except in place. And they're incompressible. Okay? Gases. Gases are fluid. That means they can flow. They are not dense. That means their particles are far apart. They are compressible. That means you can squeeze them together. 6 and 7 are talking about kinetic energy again. An object that has a high kinetic energy has a high temperature. Think of the stove and you have one of those metal coil stoves. You see that stove glowing red hot or orange. That means it has high kinetic energy. Those particles in that steel are vibrating really, really, really fast and therefore has a high temperature. An object that has a low kinetic energy has a low temperature. Okay? Well, here's your phase change diagram. I want you to please make sure you're paying attention to this part right here and this part right here. Because I'm willing to bet that on the test you're going to get a question like, as we add heat energy here, what happens at one of these two spots? And as you add energy going this way, and right here, you would have melting going on. See the arrow right here. Melting would be occurring here. And as we're adding heat energy to the system, this would be vaporization, okay, at that point. Okay, so please know those. Next page. Number 8. You've got to know parts of molecular theory. So you're going to have to go over these tonight. Particles are in constant, rapid, random, straight line motion, right? So gases move in straight lines. They're moving all the time. They're bouncing off the walls, you and me, in straight lines, randomly. And they don't stop. Gases have no significant volume compared to the distance between them. They're very, very small, okay? No significant volume. Collisions between gas particles and particles of container walls are elastic collisions. What that means is they don't lose energy, all right? That's what that means. They do not lose energy. Excuse me. All right, so now we have these words to deal with. We have temperature, absolute zero, volume, and pressure. The force per unit area. Force per unit area is the key exerted by gas particles when they collide with the wall's container. That is pressure. All right? That's pressure. The greater the number of collisions, the greater the pressure. All right, number 10. The space that matter occupies, well, that's volume. Okay? Cross that one off. The point when all motion stops, That's absolute zero. Okay, absolute zero. The measure of average kinetic energy, stupid cat, get out of here. The measure of average kinetic energy is temperature. Okay? Pretty simple. All right. The total pressure in a flask which contains hydrogen gas at 0.237 atmospheres, nitrogen gas at 0.139 atmospheres, and oxygen gas at 0.675 atmospheres, well, that happens to be Dalton's law of partial pressures, okay, of partial pressure. And all that means is add up all your pressures. So you have 0.237 plus 0.0 plus 0.139, I'll circle those, plus that, plus 0.675. When you add them all together, you get 1.051 atmospheres, okay? All right. Okay, if the temperature of a gas remains constant, number 14, what will happen to the pressure if the volume is decreased? So you're looking at a couple laws, one law, excuse me, a couple variables here, pressure and volume. Well, that happens to be Boyle's law. And so when you look at Boyle's law, and it's P1 times V1 equals P2 times V2, that is an indirect law, inverse. The graph looks like this. So if the volume is decreased, the pressure will increase, okay? If one does one thing, the other does the other. One goes up, one goes down. So, one increases, one decreases. Okay, number 15. Nitrogen gas occupies a volume of 2 liters, that's a volume, at 0.95 atmospheres, that's a pressure. What volume will it occupy at a pressure of 5 atmospheres? That's another pressure, of course. So we're trying to find V2. So the law, again, is Boyle's law. That's P1 times V1 equals P2 times V2. Makes it a little bit bigger. So V2 is going to equal P1 times V1 over V2. Okay, that's how you rearrange it. And so we substitute our numbers in, our values, and that would be 0.95 times 2.10 divided by 5. When you calculate this out, you multiply the top and divide by the bottom, you get 0.399, okay? And that would be the volume, and that would be liters, okay? Number 16. The volume of air inside car tires in the winter decreases. What causes this volume to change? If we've ever had, it's been hot, and next thing you know, the next day is like super cold, that you notice that you might get a notice in your car and a dashboard that says your tire pressure is low. And it may jump from 35 all the way down to, say, 30. Okay, that's pretty low pressure, or lower than that. So the reason that happens is the temperature of the air, the outside air, cools the tire. And when it cools the tire cools the air inside it, and the volume decreases. Therefore, this means the volume decreases, and that means the air pressure inside decreases also. Okay? That's why. Number 17, the graph represents a relationship between volume of gas. Let me get that down here. See if I can get that out of there. There we go. Whoop. Let's go over here. The volume of a gas and its temperature at Kelvin at constant pressure. The law that deals with volume and temperature would be Charles' law. And if you look on your notes, that is a direct relationship, and the direct relationship graph Looks like B. Okay? When the temperature goes up, the volume goes up. The temperature goes down, the volume goes down. 18. Gas occupies 25 liters at 291 K. What is the volume at 275 K? Well, you have a volume, and you have a pressure. Then you have a second pressure here. Okay, so we have Charles' law again, and that's V1 over T1 equals V2 over T2. So, trying to find the volume, we're trying to find V2. V2 is going to equal V1 times T2 divided by T1. And your V1 is 25. Your T2 is 275. Oh, excuse me, let me get that out. That's T. Sorry about that, guys. That's a T. Wait a minute, I got that all wrong. My goodness, okay. Let me erase that, guys. That's a mistake on my part. We're trying to find the volume. I should have wrote V2. All right, let me go back. So V2 is going to equal V1 times T2 over T1. All right, now I'm straight. Here we go. So V1 is 25. T2 is 275. And your T1 is going to be, see, I did it again. That's T. That's T1. Jeez. 291. Okay. When you multiply all this out, you get 23.6 liters. Okay? All right. 19. Well, I see they're asking for moles. So, determine the number of moles in a gas that has a volume of 0.548 liters and 9 kilopascals and 322 K. So, since kilopascals is the pressure, we're going to use this for our ideal gas constant. Okay? So, PV equals nRT is the ideal gas law formula. So, to rearrange that for number of moles, it's going to be N equals PV over RT. And that's going to be 9 is my pressure. My volume is here. My temperature is there. And my R is right, of course, right there. So P is going to be 9. My volume is 0.548. My R is 8.31. And my temperature is 322. When you multiply across the top, you get 4.9 or so. At the bottom, you get 2675.8. You divide those two numbers, you get 0.0018 moles of that. Okay? 2 to go. Aerosol cans, number 20. Aerosol cans warn they should not be put near a flame, and they should not. Using the gas laws, what science best explains the reasoning? Well, guys, if you take an aerosol can, hairspray, deodorant, paint can, whatever, spray paint can, and you put it near heat, and if it's a lot of heat, you can expand that gas inside. It's going to increase that pressure on the inside, and if there's enough heat there, it'll create enough pressure, and it's going to explode. The answer is B. Okay? 21. The pressure of a gas in a tank is 2.83 atmospheres at 333 K. If the temperature rises and the pressure increases to 6.5 atmospheres, how hot will it get? Well, we have a pressure, we've got a temperature, and we've got another pressure. There we go. I got it right this time. This is Gay-Lussac's law. All right? And that's going to be P1 over T1 equals P2 over T2. We're solving for T2 because they're asking for how hot it will get. T2 is going to equal P2 times T1 over P1. Substituting our values, we have 6.50 for P1 for P2. My T1 is 333. My P1 is going to be 2.83. Okay. You multiply the numbers on the top, divide by the bottom. 764.8 Kelvin is your answer. Okay? So there's your review. Practice this stuff, guys, a little bit. Study, please. Make sure you bring your orange reference sheet. Okay? Bring a pencil, reference sheet, and we'll be ready to go. Good luck studying tonight, guys.